At first glance, Brownian motion looks like pure randomness, a tiny particle suspended in fluid, jittering, zigzagging, never holding still. You might expect that all those countless molecules bumping into it from all directions would cancel out, right? After all, if they're hitting the particle evenly from every side, shouldn't it just stay put? And yet, it dances, it wanders. This strange jittery behavior puzzled scientists for over a century until they realized this motion holds the key to how diffusion works, and even to the existence of atoms themselves. But it also reveals a deeper paradox in our intuitive understanding of balance and symmetry at the microscopic. Let's take a step back. Brownian motion was first observed in 1827 by botanist Robert Brown, who noticed that pollen grains suspended in water moved erratically under the microscope. He thought they might be alive, but when he tested dust particles and saw the same behavior, it became clear something else was causing the motion. But what? Fast forward to the early 20th century. Albert Einstein published a groundbreaking paper in 1905 that explained Brownian motion as the result of countless collisions with invisible molecules, the atoms and molecules of the surrounding fluid. Though individual molecules are too small to see, their collective impacts on larger particles cause the random jittering that we can see. In doing so, Einstein didn't just explain Brownian motion, he provided proof of the atomic theory itself. But here's the paradox. If molecules bombard the particle equally from all sides, why doesn't it just stay perfectly still? Why does it move at all, let alone so erratically? The key lies in the statistics of small numbers. While the fluid molecules on average exert equal pressure from all directions, the actual collisions at any moment are not perfectly balanced. Think of it this way. If trillions of molecules were hitting a wall, the net force would be stable and equalized. But if only dozens or hundreds of molecules are hitting a microscopic particle at any given moment, those collisions are noisy, unbalanced, and full of fluctuations. It's like being in a tiny rowboat during a rainstorm. Not all the raindrops hit evenly. Sometimes more hit the left side, sometimes the right. The boat drifts, rocks, spins. Over time, it appears to move randomly, but it's really just responding to a swarm of tiny, uneven forces. That's what happens in Brownian motion. The particle isn't responding to average forces, it's responding to real-time molecular chaos. This randomness gives rise to diffusion, the gradual spreading of particles from areas of high concentration to low concentration. Each individual particle follows a random path, but when you step back and look at thousands or millions of them, you see a pattern, a smooth, predictable spread, like a drop of ink dispersing in water. That's the beauty of diffusion. It emerges from chaos. Random walks lead to orderly behavior at scale. And here's something even more fascinating. The path of a Brownian particle isn't just random, it's mathematically fractal. Zoom in, and it's still jagged. Zoom in more, still jagged. The longer you watch, the further the particle strays, but in a way that follows a precise mathematical rule. The displacement grows with the square root of time, not linearly. That means doubling the time doesn't double the distance moved. It increases it by about 1.4 times. This relationship helps physicists model not just particles in water, but gas molecules, heat transfer, and even financial markets. So how does Brownian motion truly work? It's the visible signature of the invisible, a window into the frantic ballet of molecules. And the reason the particle moves erratically, even though collisions are happening equally, is because equality only exists on average, over time, not moment to moment. In each tiny slice of time, asymmetry rules. And that's enough to push the particle this way, then that. Could we ever predict the exact path of a single particle? No. It's not just unknown, it's fundamentally unpredictable, governed by probability, not certainty, but that's what makes it so powerful. Brownian motion shows how randomness at the micro level creates structure at the macro level. And perhaps that's the most beautiful part of the paradox. Disorder gives rise to order, and something as simple as a jittering speck of dust becomes proof of deep universal principles. In the erratic, chaotic zigzag of a particle, we glimpse the elegant mathematical rhythm of nature itself. Brownian motion is the erratic, random movement of tiny particles suspended in a fluid, arising from collisions with the much smaller, rapidly moving molecules of the fluid. Diffusion is the macroscopic result of this microscopic randomness, causing particles to spread out over time from regions of high concentration to low concentration. Although molecules bombard the particle from all sides on average, these impacts are not perfectly balanced at every moment, leading to unpredictable motion. Thus, even though the collisions are statistically symmetric, the randomness of each individual impact gives rise to the observed erratic movement. When observing a pollen grain under a microscope, you see it jitter unpredictably despite being bombarded by water molecules from all directions. It's like watching a small boat bob and weave on choppy water, where the waves from different directions create a seemingly random motion, even if the overall water level is calm. At the microscopic level, the incessant collisions from surrounding molecules transfer momentum to the suspended particle in a random fashion. Each collision imparts a tiny force, and while the average force over time might be zero, the fluctuations in these forces cause continuous motion. The cumulative effect of countless random collisions results in a net movement that appears erratic and unpredictable. This randomness is inherent in the thermal motion of molecules and is governed by statistical mechanics. In a liquid at room temperature, water molecules move chaotically, and their random impacts on a dust particle cause it to move in unpredictable directions. It's like being in a crowded room where people constantly bump into you from different sides. While on average the bumps cancel out, the moment-to-moment impacts send you stumbling in unpredictable ways. Brownian motion is best understood statistically. Individual molecular collisions are random, but their collective behavior can be described by mathematical laws such as the diffusion equation. This statistical approach allows scientists to predict the average displacement of particles over time despite the randomness of each collision. The erratic trajectory of a single particle can vary widely, yet ensemble averages reveal smooth diffusion behavior. Hence, the paradox is resolved by recognizing that while every collision is random, the overall effect follows predictable statistical patterns. Researchers use the diffusion equation to predict that the mean squared displacement of particles increases linearly with time, even though any single particle's path is highly irregular. It's like tracking the paths of raindrops on a window. Each drop follows a random trail, but when you average their movements, a clear pattern of flow emerges. The intensity of Brownian motion is directly linked to the temperature of the fluid, which determines the average kinetic energy of the molecules. At higher temperatures, molecules move faster and collide more frequently and forcefully with the suspended particles. This increased molecular activity results in more vigorous and rapid Brownian motion. Thus, temperature acts as a key parameter in quantifying the randomness and extent of diffusion. In experiments, particles in a heated liquid exhibit faster and more pronounced Brownian motion compared to those in a cooler liquid. It's like a dance floor where people move more energetically as the music speeds up. The higher the temperature, the more dynamic the movements. Brownian motion. Diffusion is the net movement of particles from regions of higher concentration to lower concentration, emerging from the cumulative effects of Brownian motion. This process plays a crucial role in phenomena ranging from the mixing of gases to the transport of nutrients in living organisms. While each particle's movement is random, the overall flow results in a smooth, predictable gradient. Therefore, diffusion embodies the transition from microscopic randomness to macroscopic order. The gradual mixing of food coloring in water demonstrates diffusion, as the dye spreads uniformly despite each molecule moving randomly. It's like a drop of ink dispersing in a glass of water. Individual ink molecules wander unpredictably, but over time they create a uniform color across the glass. Mathematical models, such as the Langevin equation and the diffusion equation, capture the essence of Brownian motion by incorporating random forces and statistical averages. These models allow scientists to describe the probability distribution of a particle's position over time and to quantify the diffusion coefficient. They bridge the gap between unpredictable individual behavior and predictable ensemble properties. Through these equations, the seemingly paradoxical nature of random yet statistically reliable particle movement is rigorously explained. The Langevin equation includes both a deterministic term, reflecting friction, and a random force term, successfully modeling the erratic trajectories observed in experiments. It's like using a recipe that combines measured ingredients with a random spice blend, where the overall dish is consistent even if each individual pinch is unpredictable. Brownian motion has been observed and quantified in countless experiments since its first documentation by Robert Brown in 1827. Modern microscopy and high-speed imaging techniques have allowed for precise measurement of the erratic paths taken by microscopic particles. These experiments validate the statistical models and demonstrate that while individual trajectories are unpredictable, the overall diffusion process adheres to well-established laws. Such empirical evidence reinforces our understanding of the underlying physics of molecular collisions and thermal fluctuations. High simpler video microscopy of colloidal particles in suspension consistently shows random motion that matches the predictions of the diffusion equation over time. It's like watching hundreds of tiny leaves floating on a stream. While each leaf meanders unpredictably, the overall flow of the stream is smooth and predictable. The key to understanding Brownian motion and diffusion lies in the interplay between microscopic chaos and macroscopic order. Even though the individual motion of molecules is highly chaotic, the large number of such interactions results in emergent behavior that is smooth and predictable. This duality is a central theme in statistical mechanics and underpins many natural phenomena, showing that disorder at a small scale can lead to order when viewed from a larger perspective. The predictable spread of a drop of dye in water, despite the random motion of individual molecules, exemplifies how microscopic chaos leads to macroscopic order. It's like individual conversations at a busy party may be chaotic, but the overall hum of the crowd forms a consistent background noise. Understanding Brownian motion and diffusion is not only fundamental to physics, but also has implications across biology, chemistry, and materials science. Future research aims to harness these phenomena in designing smart materials, drug delivery systems, and advanced sensors that exploit controlled diffusion. Advances in nanotechnology and computational modeling continue to refine our ability to manipulate and predict particle behavior in complex environments. Ultimately, the study of these processes deepens our appreciation of how random microscopic events can govern large-scale orderly outcomes. Innovative drug delivery systems use microcapsules that rely on controlled diffusion to release medication gradually, ensuring sustained therapeutic effects. It's like designing a timed leak garden sprinkler system where the unpredictable motion of water droplets results in a perfectly watered lawn over time.